Okay, now that we've checked the valve clearances on our R6 race bike build, we've made the decision to adjust those clearances, and I wanted to explain why. It's probably two parts. Firstly, the clearances checked on the bike, they're definitely well within tolerance and within spec as per the OEM manual. But looking at the numbers, it's likely that after 6 to 12 months of track work, the bike's going to need to have the clearances adjusted anyway. So we thought, well, one of the reasons is so that we adjust them now, saves us having to do it down the track. But the bigger reason we want to do it, or the primary reason we want to do it, is actually for rideability of the bike and the throttle connection, so giving the rider a much better throttle connection. So the reason why valve clearances have an impact, I'd like to explain, and I'll just simply go through, in simple terms, first the 4 strokes of the engine for anyone who's unfamiliar with them, and the reason why like a bike like the R6 is called a 4-stroke engine is because of the 4 strokes. The first stroke is the inlet stroke, where the inlet valve's open and the fresh inlet charge, being the fuel and the air, are sucked into the cylinder. Then the second stroke, in that situation, the piston's on the downward travel. The second stroke is compression, where the piston's going up. Both valves are closed, the exhaust valve and the inlet valve are closed, and this stroke compresses the mixture, so it's taking that charge, the air and the fuel that's been allowed into that big space, then compressing it, making it highly flammable. Then the power stroke, where just before the power stroke, the spark plug ignites that fuel and air, and the explosion forces the piston down, and that's where you get your actual power from. And in that power stroke, same as the compression stroke, both valves are closed. So in both those strokes, the valves are closed. Then the last stroke is the exhaust stroke, where the exhaust valve opens and the leftover exhaust gases leave through the exhaust valve and out the exhaust pipe. So that's a simplistic overview of how the engine operates. For the purpose of this discussion, I want to speak about a little bit more detail about what's called the overlap between the exhaust stroke and the inlet stroke. So after this exhaust stroke, the new inlet stroke, the inlet stroke starts again. So it just continually repeats in that process. So with every engine, it's not like the exhaust stroke finishes completely and then the inlet stroke starts on its own. There's actually overlap in all of these strokes. So when we look further detail down here, and in this period where an engine turns is called overlap, the exhaust valve is closing. It's not quite closed yet, but it's closing. There's still exhaust gas escaping through the exhaust pipe, and the inlet valve is actually already opening. So they're both not open much, but they're both open a little bit. And it's actually on purpose and creates more power to do this. And the reason being is the exhaust gases escaping the cylinder, the suction created by that, actually helps draw new charge in, so new fuel and air in through the inlet valve. So if that was completely shut, you wouldn't have that sucking effect. So when an engine revs faster, so if we're talking about low revs, say 3,000 RPM, these strokes are happening relatively slowly. When you start revving a bike to 15,000 RPM or 16,000 RPM, these strokes are happening extremely fast. So at that point, the exhaust gas helping suck the inlet charge in is really important. That actual process is known as scavenging, and the higher the RPM, the more you require it. Now the thing is, we're about balance in an engine, and all engines are a bit of a compromise. These days you're seeing the advert of variable valve timing, and we won't really touch too much on that, but variable valve timing makes the compromise a lot smaller so that the engine can work better in most situations. But in this particular case, if we had full throttle at 15,000 RPM, with full throttle, we're obviously trying to get a lot of air and a lot of fuel in because we're trying to make the bike go really fast and using all its power. But if I've only got 5% throttle per se, I'm not putting much fuel or air into the engine. So the engine, the camshaft is designed to be a bit of a balance of both, but if the engine was designed to be perfect for 100% throttle, getting all that charge and fuel in, there'd be quite a big scavenge or quite a big overlap. So that would mean that the exhaust valve and inlet valve will be open a long time together to help this drawing process to draw as much in as we can. And that would be great for full throttle. The problem with that is if I've only got 5% throttle, because I'm only adding a little bit of air and fuel, I'll lose it all in the exhaust pipe. None will actually go in the combustion chamber, meaning that this compression stroke will have hardly any fuel or air and the power stroke will be very weak. So in that situation, if we had it designed perfectly for full throttle, the bike would almost be like an asthmatic on the small throttles. It wouldn't want to actually do anything. It wouldn't have much power. And that's characterised by bikes that can have an abrupt throttle. So that, and the reason being, you might think it's got an abrupt throttle you would relate to, it's too much power initially. It's actually normally the other way, and what's happening is that 5% is not doing much. So as a rider, you actually pull more, and you might pull it to 10 or 15%. And when you do that, that's when it comes on abrupt, because all of a sudden, the characteristics of the engines catch up and it starts performing. So that you get this all nothing, then all of a sudden, whoa, it starts going. So for a really rideable bike, it's, you know, especially if you're in the middle of a corner, you're on the limit of grip from your corner speed, you want that throttle pickup to be really smooth and really gentle, so that you're not getting, you know, sudden loss of grip or the bike unbalancing itself with the power. The bigger the engine, the more critical this gets. You know, in a 600 it's quite critical because it's quite powerful, and in a 1000cc bike more so because of the power that they have, and you know, an aggressive throttle or abrupt engine is going to upset the chassis and the handling quite a bit. So it's a compromise. What we look to do is come up with valve clearances that, and I'll backtrack one step. Valve clearances only affect this to a small degree. If you've ever heard about valve timing and changing the valve timing that you do in race bikes or full engine builds, you'll alter the timing to get your desired balance. Some engine builders have a concept where they're going for more top end power. Some engine builders will like the smaller throttle positions. Here at Race Centre we like to build engines that are easy to ride, and our concept is that the better the bike handles and the faster you accelerate off the turn and the more corner speed you carry, the faster you're going to be down the straight anyway. So we don't tend to go for top end horsepower, we go for really rideable power and bikes that are easy to get on the throttle and drive them hard off a turn, ultimately for a better lap time rather than a better dyno reading. So with that concept in mind, our rules do allow us to change valve timing, but for this specific build that we're doing, the R6, a club level racing, we're not going to do a full engine build, and it's purely based on costs. When you start to do valve timing and things like that, putting thinner head gaskets, and to do it properly, you should be pulling the engine apart properly, measuring everything, and the costs get quite high. So for this level of bike, it's not actually required, but because the valve clearances are a maintenance item anyway, we're doing that. And we can make a small adjustment to all this by the valve clearances. The reason being is, as I explained a little bit earlier, I'm going to look at an isolated drawing here. That's my valve bucket and my shim, and I talked about the cam lobe sitting on top, and then the cam will rotate and open this valve. That shim dictates, you know, that clearance. If I make that clearance bigger, in this part where we're scavenging, the valve, or that particular valve, will be open less. If I make the clearance smaller here, in that part the valve will actually be open more, because the cam's not changing, that gap's, I'm moving essentially where this valve is, so I'll open or close it more or less. So that gives us a bit of scope to adjust this area. So the biggest reason why we're doing the valve clearance adjustment on this bike is to get us a much better throttle connection than it would currently have with its clearances, and then B, to prolong the time that we're going to need to do it down the track anyway. For those of you, and you know, just to demonstrate how important this part of it is, and while this part on a dyno is actually very hard to check the power differences because it's such small throttle positions, but it is very noticeable on a racetrack. If those of you can remember way back to 2007 in MotoGP when they first went to 800cc motorbikes, if you remember, the Ducati was an absolute rocket ship in a straight line. Once they got going down long straights, it passed anything with will and ease. The primary reason for that was what they also did when they went to 800cc in 2011, they brought really heavy fuel restrictions in. So on full throttle, if you're using a lot of fuel, it was going to hurt you over the race distance. What Ducati did with the help of without Shell and Ferrari is they stole fuel away from this part when the throttle's closed. They were the first to really develop fuel saving in that area, or to maximise it. So they actually took a lot of fuel away when the throttle was closed, or when you to save fuel over the race distance, so that when the rider had the full throttle open, the bike was really fast in a straight line. The trade-off for that, if you remember, when they did that, most riders could hardly ride the Ducati back then, and it was only Casey Stoner, who was a bit of a freak, that could actually ride that bike. And a big part of that, and what riders complained about in that era, was the abrupt throttle connection with the Ducati. And it was because they were taking fuel away from that. To a lesser degree, if you had poor valve clearances and this charge was going in the exhaust, you're doing the same thing. You're making an abrupt throttle, and it'd be hard to ride, and only really talented riders are going to be able to ride a bike like that. And we certainly don't build them like that, because for our general customer base, it's about having bikes that are easy to ride fast, and we certainly don't have any fuel saving restrictions, so there's just 0 point to take the fuel away from that area.